Welcome back to the deep dive. Today, we're really tunneling deep into a pretty specialized and frankly quite brilliant corner of computational physics. Our mission is to analyze some source material focused on building highly efficient numerical models, specifically for constrained fluid dynamics. And we're really zeroing in on this mathematical concept of divergence-free spaces.
Right. And for you, the listener, this isn't just abstract theory. Uh, this kind of work is absolutely fundamental. It's fundamental to simulating one of the most common yet complex phenomena out there, incompressible flows. These are flows where the fluid density, the volume, essentially stays constant, and they show up everywhere.
Everywhere is right. We're talking about massive critical simulations here. Think about modeling how oil moves through complex rock formations, that's petroleum reservoirs, or predicting how contaminants might spread through groundwater aquifers, that kind of thing.
Exactly. And beyond just porous media, this framework is crucial for solving some of the really big, enduring equations in physics. Things like the Navier-Stokes equations or the Sinclair-Stokes equations. So if you want, say, accurate long-term weather forecasts, or you need to model airflow around an aircraft wing, or even analyze fluid movement through complex pipe systems, like in chemical engineering, well, this type of specialized modeling is really the bedrock.
Okay, so the real-world stakes are definitely high. Let's define the core mathematical challenge, the constraint they had to wrestle with. That's the divergence-free constraint, right?
That's the one. Mathematically, it's just a very elegant way of saying the fluid is incompressible. Imagine flow going into a small volume, like a little box. The same amount has to flow out. There's no buildup, no compression or expansion inside that box. Divergence is zero.
Simple concept, but computationally tricky to enforce, I gather.
Oh, yeah. And here's the core pain point that really plagues the traditional methods. Usually when you want to enforce a constraint like this, like incompressibility, you end up using what's called a mixed formulation. You basically introduce an extra variable, usually the pressure, and then you use something called a Lagrange multiplier to couple it back to the velocity field. And the result, structurally, is what's known as a saddle point formulation.
Okay, saddle point formulation.
Yeah.
Why does that term sound like bad news in the numerical world?
Because they are notoriously difficult.
Right.
The linear systems you get from them, they aren't nicely invertible like standard problems. They're non-positive definite, and they can be inherently unstable unless you're extremely careful. You need these really strong compatibility couplings like the LBB condition or INTHUP condition between your pressure space and your velocity space. If you don't pick those function spaces just right, and sometimes it's quite counterintuitive, the solution can just blow up or give you completely garbage oscillating results.
Sounds like a huge drag on actually getting reliable simulations done. Okay, so let's unpack this then. The mission laid out in the sources we looked at is essentially to sidestep that entire painful process.
Exactly.
The authors wanted to develop a specialized finite element approach using something called Rham sequences to build that divergence-free constraint right into the design. The goal being presumably faster, more stable simulations that are easier to solve.
That's precisely it. And to really appreciate their solution, we kind of have to start with the mathematical foundation they built upon. That's these exact finite element de Rham subcomplexes. It sounds complicated, but it provides this beautiful underlying structure. It shows how different types of function spaces are related to each other through the fundamental differential operators.
So function spaces. So we're talking about defining what kinds of mathematical functions are allowed in our model.
Yeah.
Right? Based on how smooth or differentiable they need to be.
Exactly. We're dealing with spaces like h1, h dollar omega. These are functions that need to be continuous, and their first derivatives have to be square integrable, reasonably well behaved. Then you have these vector spaces like h curl omega, where the vector field itself might be a bit rough, but its curl has to be well behaved, square integrable. Similarly, h-div, h-eniga, where the divergence needs to be well behaved. And finally, the most basic one, L2 omega, just square integrable functions, potentially quite discontinuous.
And this sequence of spaces, you said they're linked by the standard operators we know from calculus. Gradient, curl, and divergence.
That's the chain. You take the gradient of an h$1 function, you land in curl cuck. You take the curl of an h-curl function, you land in h$1. You take the divergence of an h$, you end up in Talato function. And the core geometric property, the thing that holds these complexes together, is actually stunningly simple when you think about it. The composition of any two consecutive operators in that sequence must be zero.
Ah, right. Like the curl of any gradient is always zero.
Exactly. And the divergence of any curl is always zero. It's fundamental vector calculus identity baked right into the structure.
So these operators are kind of like filters. They refine the space at each step, throwing away certain kinds of functions.
You could think of it that way. And the real power, the magic, comes from this property called exactness. Exactness tells us that ideally, the range, meaning the output of one operator, is precisely the same set as the null space, the kernel, the things that get mapped to zero of the next operator in the sequence. So for instance, the set of all vector fields that are gradients is exactly the same set as vector fields whose curl is zero, at least in simply connected domains.
Okay, that's a deep connection. So if we take that exactness idea and apply it back to our incompressible flow problem, we need the divergence to be zero. How does that map onto the sequence?
It maps beautifully. Our desired divergence-free finite element space, let's call it a $V gamma, is defined precisely as the kernel of the divergence operator. It's all the functions in our flux space, V like a rho, whose divergence is zero. But here's the crucial link, thanks to exactness, particularly in 3 dimensions. This kernel, V gamma, is also guaranteed to be the range of the curl operator, acting on the space just before it in the sequence, the HA's curl space, 6 gamma.
Wait, so instead of adding extra equations and Lagrange multipliers to force the divergence to be zero, we can just define our solution space to be the set of functions that are already guaranteed to have zero divergence because they're constructed as the curl of something else.
That's the conceptual leap. It's incredibly elegant.
Wow, okay. That seems, well, almost too good to be true. If this connection range of curl equals kernel of divergence is known from the de Rham complex theory, why wasn't this the standard approach all along? Why did people keep struggling with those difficult saddle prime problems?
Well, the difficulty shifts. It becomes entirely practical and computational. The real challenge lies in actually constructing a basis for this divergence-free space V gamma, and crucially, a basis that's linearly independent.
What do you mean? Why isn't it straightforward?
Well, if you just naively take a standard basis for your curl space, 6 gamma, and you apply the curl operator to every single basis function, the resulting set of vector functions is guaranteed to be divergence-free. Yes, that part works. But that set will contain massive redundancy. Many functions will be linear combinations of others. It won't be a minimal efficient basis.
Okay, why does that redundancy creep in?
It happens because the kernel of the curl operator itself isn't trivial. Remember, the curl of any gradient field is zero. So any basis functions in your original curl space that are secretly representing gradient fields, well, applying the curl operator just maps them to zero. They don't contribute to the final divergence-free space. But also, combinations of basis functions can represent gradients. These gradient fields are essentially redundant information for constructing the curl space. And this problem, this redundant space of gradients, gets bigger and more complicated as you use higher-order polynomial elements.
I see. So you generate maybe loads of vector functions, but many of them are either zero or aren't actually adding unique information to the solution space. And dealing with a basis that's not linearly independent would just kill the computational efficiency you were hoping for, right?
Exactly. It completely undermines the potential gain. You end up with huge ill-conditioned matrices again, just of a different kind. And that brings us directly to the core innovation in the sources, this specialized filtering process. Think of it like a surgical strike. They figured out how to remove the mathematically redundant parts before applying the curl operator.
Okay, tell me more about this filtering. The idea is to carefully remove specific shape functions from the original curl basis, 6 gamma, before taking the curl.
Precisely. The goal is to select a subset, a much cleaner basis, set within 6 gamma. You prune out exactly those basis functions or combinations that would only generate gradients or map to zero when you apply the curl, so that when you do finally apply the curl operator to this filtered set, the resulting basis for the divergence-free space is mathematically guaranteed to be linearly independent, minimal, and efficient.
Clever. It's like pre-processing the ingredients. And this wasn't just one filter, right? The authors described 2 different filtering stages.
That's right, because the redundancy shows up in different ways depending on the polynomial degree of the elements. The first one they describe is spanning tree filtering.
Okay, spanning tree, like from graph theory.
Exactly like graph theory. This is a global algorithm, meaning it considers the whole mesh. It's specifically designed to filter out the redundancy associated with the lowest degree upper curl basis functions, the ones associated with the edges of the mesh elements. The problem here is that if you take all the edge functions, you can combine them to globally represent the gradient of a scalar function, defined at the vertices, the simplest kind of gradient field redundancy.
So you need to remove just enough edge functions so you can't represent any arbitrary gradient anymore.
That's the intuition. The spanning tree provides a systematic way to do it. You pick a root vertex, say a bar. Then you build a spanning tree connecting all vertices. You then discard one edge function for each edge that belongs to that spanning tree. Geometrically, this removes exactly the right number of degrees of freedom, number of vertices minus 1, to prevent the representation of a global potential field, up to a constant, ensuring the remaining edge functions, when curled, only generate the needed non-gradient fields.
Wow, okay, that's a really neat connection between graph theory and finite element basis construction.
It is quite elegant, but that only handles the lowest order redundancy. For higher order elements, using polynomials of degree k dollars, things get more complex. That's where they introduce the local filtering process.
And what's this local filter targeting? More complex redundancies.
Yes. This one operates at the level of a single master element, like a reference triangle or tetrahedron. Its job is to identify and remove the higher degree basis functions, those associated not just with edges, but also with faces, and the interior of the element that could be combined locally to represent gradients of higher degree scalar polynomials. These are more localized gradient field redundancies that also live in the kernel of the curl operator and need to be removed.
Got it. So you've got this global spanning tree filter for the basic stuff, and then this local filter for the higher order complexities. Every potential source of gradient junk is surgically removed before you hit it with the curl operator.
That's the idea. And just for context on implementation, the authors mentioned they built and tested all this using NeoPZ. That's an open source, object-oriented C++ library, which kind of speaks to the fact that managing these filtered basis functions and element operations isn't trivial code-wise. You need good software structures.
Right. Makes sense. Okay, so after all that careful mathematical and algorithmic work, let's talk about the payoff, the computational bottom line. You said this avoids the big, nasty saddle point system for incompressible Darcy flow. What replaces it?
What replaces it is beautiful. You get two consecutive, much simpler problems to solve. First, you solve directly for the flux field, the velocity. Because we designed the function space d to dot so carefully to be divergence-free and have a linearly independent basis, this step becomes a standard Galerkin variational problem. It results in a symmetric, positive, definite linear system, the kind we love to solve.
Positive, definite. That's the holy grail, isn't it?
Yeah.
Much easier solvers, guaranteed solutions. That alone is a huge win compared to saddle points.
It's a massive win. That's the game changer right there. No more need for complex, specialized preconditioners for indefinite systems. And then once you have the flex field, the second step is just computing the potential or the pressure. And that turns out to be a relatively simple post-processing step. You already have the flux. You just need to solve a Poisson-like equation to recover the pressure that's consistent with it. This sequence solve for flux, then post-process for pressure is inherently more stable and numerically far, far easier to handle than tackling the original coupled saddle point system head-on.
Okay, now here's where the proof is in the pudding. The numerical tests. Did this reduced formulation actually deliver efficiency gains without messing up the accuracy?
Absolutely. The results reported were really clear on this. They ran verification tests using known harmonic solutions. And the reduced formulation, let's call it RF, produced results with the exact same errors, and critically, the exact same predicted convergence rates as the traditional standard mixed formulation, SF. So if theory predicted the error should decrease like order IK plus 1, 1 as the mesh size dollar got smaller, both methods achieved that rate perfectly. Accuracy wasn't sacrificed at all.
Okay, same accuracy, same convergence. But the efficiency, how much smaller did the problems actually get?
That was the really impressive part. The size of the linear systems, measured by the number of degrees of freedom, df, was drastically reduced. In their 2D tests, the def reduction was significant, somewhere between 55% and 65%, depending on the polynomial order used. And maybe even more importantly, in 3D, where computational cost just explodes, the reduction was still huge, reported between 45% and 50%.
Wow. So you're solving essentially the same physics problem, getting the same quality answer, but using roughly half the variables.
Pretty much. That's a phenomenal shortcut, right? Achieved purely through smarter mathematics and geometric construction, not just throwing more computer power at it.
That really underscores the power of choosing the right mathematical space.
It does. But as always in computational methods, there's often a catch, or at least a detail to handle carefully. Boundary conditions.
Ah, yes, the boundary.
Yeah.
Especially Newman conditions, where you specify the flux across the boundary. Did the new method handle those okay?
Well, the paper noted an interesting subtlety there. If they just used a simple standard approach to enforce that flux boundary condition, like adding a penalty term, they called this RF plus P.
What happened then?
Things started to wobble a bit. They observed in a benchmark called the five-spot problem, which is a classic test for simulating flow in porous media reservoirs, that this simple penalization, RF plus P, actually led to a noticeable loss of accuracy as they refined the mesh. The convergence rates weren't as good as expected. It seems like rigidly forcing the flux condition on the boundary conflicted somehow with the global constraints built into these divergence-free spaces.
Okay, so simple penalization wasn't robust enough. What was the fix? Did they have to go back to Lagrange multipliers?
Sort of, but in a much more targeted way. They needed a method that could impose the flux condition weakly without messing up the internal structure of the divergence-free space. The robust solution turned out to be using a hybridization technique. Let's call it RF plus H. This did involve introducing a Lagrange multiplier, but crucially, only on the boundary of the domain, not everywhere inside. This boundary Lagrange multiplier was used just to weakly enforce the Norman condition, and bingo, that approach immediately recovered stable and accurate flux results, matching the expected convergence rates again.
Okay, that makes sense. It's like a compromise.
Yeah.
They avoided the big domain-wide saddle point headache, but they accepted using a small localized Lagrange multiplier just to handle the boundary fluxes cleanly.
Exactly. It's about using the right tool for the right part of the problem. And one last thing on flexibility, the authors also showed this wasn't just limited to flows where the divergence is exactly zero everywhere.
Oh, how did they generalize it?
They demonstrated the methodology could be extended fairly easily to handle cases with a non-zero but constant divergence. This is relevant for simulating sources or sinks in, say, heterogeneous porous media. You just slightly modify the space construction to search for the flux in what they called a constant divergence space, phi gamma. It shows the underlying framework using the de Rham complex filtering basis functions is pretty general and adaptable.
Right, so let's try and synthesize the central takeaway here for you, the listener. This work really provides an incredibly efficient and, importantly, robust way to simulate these physically constrained systems, like incompressible fluids. And the key was designing these highly specialized mathematical approximation spaces, the divergence-free spaces, that basically bake the physics constraint right in from the start. It eliminates a major source of numerical instability right at the foundation.
Absolutely. And I think it raises a really important point. By digging deep into the underlying mathematical structure, the de Rham complex, and combining that with clever geometric ideas like the spanning tree filter, they managed to transform what was a fundamentally difficult, often unstable saddle point problem into a sequence of much nicer, positive, definite problems. It really confirms that sometimes designing the right mathematical space is even more critical than just having the fastest computer hardware. You don't necessarily have to trade precision for computational efficiency if you're smart about the formulation.
Well said. And that really leaves us with a final provocative thought for you to maybe mull over. Given that the success here hinges on this beautiful blend of advanced geometric concepts, like those spanning trees, and deep functional analysis from the de Rham sequences, what other complex physics problems out there, maybe in different fields like acoustics, electromagnetics, or perhaps even stability calculations in quantum mechanics, are currently bogged down by computationally expensive mixed formulations? What other physical system might just be waiting for someone to figure out its own custom-designed mathematical space, leveraging similar geometric or topological insights to unlock massive computational efficiencies? Maybe the next big leap in simulation speed isn't just faster chips, but fundamentally better geometry. Something to think about.